Okay, so you should be able to see my screen now. If you don't, please tell me and we will fix this problem.
Yeah, we can see it. Good. Maybe you could zoom in slightly, maybe, if it's fine.
Yeah, I'll try. A moment. Dun, dun, dun. Better now?
Yeah, that's better.
Okay, okay. So let's just scroll through a bit so I'll be aware of what awaits for us today. Oh, yeah, a lot of material. Okay, so maybe we should catch up a bit about spin and helicity. I don't know. Okay, so previously in the previous section, we've talked about spin a bit, and we said that the amount of spin is always the same. It could be right-handed or left-handed, and also spin can be any superposition of those two basic states, like anti-clockwise and clockwise rotation or something. And S quantity here is called helicity of the particle and is a half integer or integer. And in the case of the photons, circular polarization, that S value equals to plus or minus 1. And plane polarization is just some combination of those circular ones. Okay, and we just used that to describe one practical experiment here, and that the fact that helicity changed after the reflection, and that made it possible for us to state that projection postulate is actually needed to get the right result in that experiment.
I have a question about this. It's all right.
Okay.
So these null measurements seem to be the experience where they don't directly measure anything.
Mm-hmm.
But how can I see that this lines up with the model, the theory, this thing? But how could they know that there actually was a state change in the part that wasn't detected? He seems to be stating this as a fact, but how can we know this is the case and not just fits the model? How would you confirm this experimentally? I mean,
yeah, it's a hard question. Like, I don't know what to say here, but I think that like the projection.
Is he saying that it is confirmed experimentally to begin with? Is he claiming that, or am I misinterpreting it?
Yeah, like for example, I think that like the previous example with the bomb here and C detector, uh, that's kind of one of the possible experiments that could be done.
You can say what not happened, sure.
Yeah, so you can detect the presence of the C detector uh, when you will got the B detector to catch up the photon. So if C isn't isn't in the way here, then the interference will happen here, and only A detector will get the photon, like with 100% probability. And probably that's like the experiment which like could show us that like by detection of the photon at B, we know that non-measurement of that photon by C kind of collapsed this state or something. So
yeah, that's the thing, specifically what I have a problem with, that it would collapse the state, that we could say that
yeah.
with certain.
Yeah, so it seems that like mm, the potential measurement or something, like the not the possibility, like the try.
Isn't it monster?
What?
Now when I see you talking about this, I guess it makes more sense in this example than the following, that it is
Mm-hmm.
actually
Yeah, and
detected the other
in this
probability.
more simple example, it's assumed that your source and detector are perfect one. So it's just like in theory. But even if they
Yeah.
are not perfect and they kind of like 99% effective in detecting and emitting particles, I think that statistically it would be enough, like good enough to confirm. And yeah, and probably uh, in the case of non-detection here of the tau uh, thing, then we can measure the rho here with rho measurement, like place the rho measurement detector in the way of the rho wave function, and we will have like 100% uh,
Yeah,
of the raw
but
states there if tau wasn't measured or something. So that's kind of the
but, but, but but if you put a detector at a row, then you would collapse the state of row by virtue of it being measured. But the thing is here that it is not measured, and he still claims it is collapsed. It's very different if you actually measure it or not.
yeah, but that's I think like the tricky part here is that we should treat our wave function as like the whole thing, so that it's like the holicity property.
Sure, it's whole, but it is not necessarily collapsed. Or rather, it's not until it's measured, is what I thought.
Yeah, but like non-measurement is the measurement. So
Yeah, that's the weird thing.
yeah, that's a weird thing. Yeah, I don't know how to deal with that in practice, but like in theory, that's what we will get. Uh, yeah,
Okay, I think we have to move on, but thank you for addressing it.
yeah. Actually, a lot of questions could be asked about those things. So yeah, but I was only like concerned with the book material actually. Okay,
I,
so
I think the way that you can deal with it
uh-huh.
statistically is uh, using like Bayes' theorem. Um, yeah, like the probability of getting the rho state given that it's not in the tau state. I think that changes your distribution, and that's what they mean by collapse. So like Bayes, he tells us how to like adjust our distributions given an individual observation. And so even like unrelated to quantum, you can end up with a new distribution given some particular measurement. And I think that's what he's using as sort of like a proxy for wave function collapse, is that, well, given that you didn't measure it at tau, the distribution now has a different shape, and it's all at rho.
Okay, I think I'm starting to begin seeing what you're saying here. Yeah. But that is a different distribution. I'm not sure exactly what that means, but I would say that it would have a different statistical result if it was not measured there, sure. But that it would have a definite state being collapsed, that's where I have a hard time understanding it. But that the result would be different for sure.
Yeah, maybe I need to like make a new document and add some questions there, maybe for laters. And that one is like null measurements in practice or something.
Yo, maybe I'm completely misunderstanding this, but are you saying that by virtue of it not being measured, then the what is it, the row one that was not measured, will that one be collapsed on average? And that's why we're saying it's collapsed, because it's statistically the most likely.
Yeah, I see what you mean. So if these are perfect detectors, then it would just purely collapse onto the rho state, right? Say we have a two-state system, there's tau and rho, and if these are perfect detectors, then given that you did not detect it at tau, it will necessarily be in the row state, right? And that's actually just a statistics thing, not necessarily a quantum thing. And so the relation between quantum and statistics here is that you can get a probability distribution if you square the wave function. So you basically are doing this like Bayesian updating on the wave function, but it's really on the square of the wave function. So there's a slight disconnect there.
Yeah, that was really helpful.
I need to learn more about Bayesian theorem. I always like skip the topic in university. Okay, so and in the next section we talked about like basic structure of the Lie algebra for rotations and its generators, and that those could be connected to the like angular momentum components, uh, observables basically in quantum mechanics, and that one of the representations for those we could have is the Pauli matrices, and it is like the simplest non-trivial representation which will give us spinors. And we talked about spinors also a bit, that uh, if you open the book, let me open it and jump a bit here. Yeah, and we also have seen that like it could replace like a tensor calculus, and we could have like a spinor calculus or something. Yep, and we can have like different spin values, and for different spin values we will have more elaborate spin tensors, which are not like forced to be spinorial ones actually. So they will be spinorial only in the odd n case here, so when spin is not integer. But anyway, it will form kind of spin tensor here, which is symmetric in its indices, ABF here, and it will have n indices and n plus 1 independent components. Yeah, and here was something about representation theory. Okay, yeah, so basically this subchapter ended with the comment that like for spin zero particles called scalar particle like p meson, the wave function has zero indices, zero like spin indices, and that means it's just a scalar, and that's the situation that was treated in chapter 21, so with our like Schrödinger equation, etc. And the most familiar particles, they will have spin 1/2 and we'll have just one index, so we will have like one spinor, and that will have like two components actually, which we've seen on the previous page here. I have thought that we should have seen that. Okay, probably no. Yeah, so it is here like psi 0 and psi 1. Okay, great. So it's just like two components for one spinor index here, and that's why it always seemed to me. So I've seen like quantum systems before in quantum programming, and I didn't know that those were spinors. So I always treated those like vectors and actually worked with those like the same way I will work in like a Hilbert space or something. So I just could like could be not aware of that like more complex nature and just work with probabilities and make some programs just work. And yeah, so and in more elaborate cases, general ones, yeah, for like general spin here, we'll have that n component spin tensor with n plus 1 independent complex components inside. Yeah, and that scene is frequently related as an index spinor, but it is not a spinorial object, as I have said already, and it is spinorial only when n is odd. Okay, yeah, and here it's also remarked that like spin value itself is determined by the eigenvalue for the total spin operator j squared here, which commutes with each component L1, L2, and L3 here for the angular momentum. And this property characterizes G squared as a Casimir operator for SO3. Yeah, and we need to form what is called like complete set of commuting operators. We will talk, I hope we will have time to talk about this today, later. And then we just look for the states that are simultaneously eigenstates for all the operators of this set, and we can kind of label or like create a basis for wave functions from those, like from the eigenvalues for those operators from the complete set of commuting operators. Yeah, and J value, like for the spin, arises as the eigenvalue of the G squared operator here, and M is the eigenvalue for the angular momentum along the Z axis, and it will have different values between minus J and J here. Yeah, so that's it, and now we can kind of go into the further material. And the next theme to discuss here is the Riemann sphere for the two-state quantum systems. And two-state quantum system is described using like h squared space, and like spin 1/2 particle nicely represents its geometry. So for spin 1/2, as we have seen already, we have like two components for the spinor, and we are working in particles rest frame here, so components of spinor will be constant, and then that means that we can represent it like the overall state just as two complex numbers W and Z, and that's it. And we can fix like up state as 1, 0 here, and down state as 0, 1 as a basis for our space, and therefore we will have like a general state described in terms of the basis and WZ coefficient there as superposition, and for any two general states like AB and WZ we'll have a scalar product, and we will be able just to like take it like that, where star is complex conjugate for A here. Yeah, and every spin 1/2 state is a pure state for some direction in space, so it doesn't depend like what state we are in. We can also make it a pure state when we choose the particular direction in space, and this gives us a nice identification between the projective geometry of the h squared space and the geometry of directions in space itself, and different points of the pH2 are just ratios, not ratios, just ratios of complex numbers like W over Z, and therefore they are just complex projective space of dimension 1, and that's like the space of or 2, I don't remember exactly. So I'm not sure about this. Am I right here that Riemann sphere is complex projective space 1, or is it complex projective space 2?
Yeah, it would be CP1 because
CP1,
you have
yeah.
the complex plane that gives you 2 dimensions, and that you can project down from that pole, right, all the way at the bottom, the down state. They're doing a stereographic projection. So this is just for one complex number. You can do this projection from the Riemann sphere onto the complex plane.
Okay, great. So then I was remembering correctly while I was writing these summaries. So stereographic projection from a south pole to equatorial plane, as on the figure below, connects the directions in space to the corresponding ratios. Why ratios? One moment. Ratios here and ratios. Yeah. So this stereographic projection for that state, like arrow on the side here with that point on the sphere, will give us a point u, which actually equals to w over z ratio. So we will get those ratios from the directions in space basically by stereographically projecting those from the south pole here. And we should note here that orthogonal in the Hilbert space we are working does not correspond to the at the right angle notion, but it is true for the opposite vectors. So our vectors like up and down here are orthogonal. And if spin state is initially in some state like that, like arrow to the left, then the probability to get some other state with that other direction, arrow to the right, after measurement depends on the angle theta between those and could be calculated by using that formula with cosine here. And Penrose includes like geometric proof of that fact, where he just like projects the point B here to the point C line on the AO here, and A and B thinks they're just like those two different states we are in. So we kind of project in one state on the another, and after obtaining our like projection here, we need to divide the right things. So I'm not sure why, but he just says here that we need to divide like the by taking the opposite point here, A with tick here, that we need to divide A tick C by A tick here. So like the whole length will divide that smaller one, A tick C. Yeah, so and here he says that like the complex numbers, they are not completely abstract things in quantum mechanics, and in this case, yeah, and they are related to the dynamical phases as we know, and also to the geometrical behavior, and the geometry of the CP1 is quite general for the two-state systems. And what is special in the spin 1/2 case is that we have the immediate association between special rotations and the points of the Riemann sphere. And in other physical situations, the geometrical role of that sphere and complex numbers is not very direct, and there is a tendency among physicists to regard those as mere formal quantities. And this attitude arises partly from the fact that the overall phase of the state vector for entire physical system is considered non-observable, but we know that relative phases between one part and another certainly play an observable role, and one way of expressing that is the fact that the geometry of of the projective space H can be used as the basis for quantum mechanics where only global phase is taken out, but relative phases feature in its geometry. So I put some question marks here because that's kind of really brief description, but like basically what it says that we can build the quantum mechanical theory on pH, and pH is just taking out from the consideration the global phase. So basically we divide taking ratios for all these states in the Hilbert space H, and therefore we kind of remove the global phases from everywhere. But relative phases, they will be a part of its geometry, because relative phases is kind of the relative or relations between the parts of a system or something. So they will kind of have the impact in our formulas and probabilities, etc. Yeah, and this page actually ends with the part about polarization states. And we have seen already that in general there are superpositions of the positive and negative felicities, and are elliptical in terms of polarization, and simpler cases include circular or linear cases. So in general, the quantum state here is W plus Z minus states. And to understand that, we can take a look at the form of the electromagnetic waves on the pictures below. So we always have electric and magnetic field vectors which are always perpendicular to each other. And at the picture A here, first one, you can see the plane polarization, and that means if you imagine keeping a point in space fixed and allow the wave pass by, then the electric vector will just swing. So it just will grow out in a line and then will grow down, then grow up and then grow down, and it will be contained inside one line, and that means the linear polarization. But if the electromagnetic wave has more elaborate structure, like on the picture B here, here we have constant turning of the electric field and also magnetic field, therefore, because angle between those is always 90 degrees. So you will see a nice circle in the standing wave plane if you fix some point in a space along the wave. So electric field and magnetic field will just run in circle, and you can see that on the picture C at the bottom here. And on the top you see the more general case for the elliptic polarization, where electric field goes in one ellipse and magnetic field goes into other one ellipse here. Yeah, and now we can use Riemannian sphere to obtain the polarization ellipse for our quantum state here. And to do this, we need to take square root of our ratio Z over W here, which will lie here or give us the direction in space, the Stokes vector. And if we draw a great circle.
Sorry.
Yeah.
Maybe I'm nitpicking here, but aren't they both circular polarizations, just that the combination of them gives an elliptic result? It looks like that to me. They seem to be individually circular, but the combination of it gives this elliptical skew that we see in the next illustration. Maybe I'm totally off here.
Yeah, maybe you're right. Let's take a look. So here it says that lower figure shows the circular polarization, okay, and the upper one for the general case of elliptical polarization, the heads of two arrows tracing out congruent ellipses with perpendicular major axis. And single photons wave function could exist. So it seems to me that text here is saying about ellipses here.
Yes, but the components would be circular, but the combination would be elliptical, is what I'm claiming.
Yeah, but like on the picture, those are not circles, right?
That's what I think they are individually. Yeah.
Yeah.
I think you're right, because it becomes an ellipse when you project it. Like, they're both circles on the Riemann sphere. They're great circles. But then you project it into the complex plane and they become an ellipse. I think it's on this next figure, Slava.
Yeah, exactly.
Yeah, so they're both great circles. And then you project it into the plane and you get an ellipse.
So by using that Stokes vector, we are finding like this like pure circular polarization here.
Yeah, I think that's right. And then when you project it into the plane of the equator, that's where we end up with the ellipse. Because the ellipse depends on the angles between these two great circles.
So like those two circles will like intersect in different angle, but that's not true, right?
Yeah, where this is confusing for me is that E and B are always perpendicular.
Yeah.
So I see what you're saying there, because like if these great circles weren't perpendicular from each other, then E and B wouldn't be perpendicular. But it seems that in this figure that they're not necessarily, because we end up with an ellipse rather than just a circle.
But maybe like we have like two square roots here, right? Like, and he said in the book that we can take any of those, and maybe like the other square root will give us another big circle here, or the circle will be the same. Maybe it will be just perpendicular. Yeah, it should be perpendicular.
I would guess that it's perpendicular.
It should be also perpendicular to the same circle, yeah. Strange. Okay. Yeah, anyway, so yeah, I do not understand that in the details. That's true, but anyway, like the overall scheme seems like described briefly here. So I think if we will need something like more detailed on those matters, we will be able to dig into it later. Maybe you have some questions about this subchapter? Yeah, okay, so the next subchapter is about higher spin. So here Penrose want to consider spins for the higher values for n here, like n over 2, for massive particles. And they will be represented with an index spin tensor. I wrote it here like psi with that like underline here, meaning like indices like ABF here. And he says that there is a theorem which guarantees that we can have like a canonical decomposition for those in terms of the symmetrized one index spinors. So we have like for each index here one spinor, like alpha, beta, and phi here, and they are all symmetrized by the ABF indexes. And therefore, we can represent the general spin tensor as a set of points on our Riemann sphere as n unordered directions in space. So we have seen Riemannian sphere here with that spin representation here, and now we have decomposed the more general spin state into number of those states symmetricized, but if we took them as like independent two state systems or like spin 1/2 systems, then they will just like be described as bunch of the directions in space. And in the same way we can construct like a standard basis for those states called Majorana basis. So it will be just from up and down directions for every spinor here, and those will be eigenstates for the L3 observable, n+1 in total, all orthogonal to each other, and they are distinguished by the m values we have seen in 22.8, and those m values will be from -j to j, and basically they will just calculate the number of the up vectors, for example, here, and or down vectors, where probably down will be, or maybe I'm not right here. Okay, so but that's kind of connected. So like all down will be associated with -j, and all up will be associated with j. Yeah, and there is a standard measuring device to measure this m value called Stern-Gerlach apparatus, and basically it includes some like strongly inhomogeneous magnetic field here, which will deflect the path of the particle depending on its like magnetic momentum vector, which is a multiple of a spin, and it will deflect like different states for a particle. So basically it acts like a measurement device here actually. So it measures the spin actually, and or like angular momentum along the L3 axis here, like L3 measurement device. Yeah, and it will deflect different m values for our particle to the like different like deflective rates or something. So you will see like lower m lower on the vertical axis here, and for the higher values of m the point will be higher. Yeah, and the orthogonality conditions for general Majorana states, they're complicated, but if some Majorana state includes direction, like some general direction to the right here, then it is perpendicular to the state which includes only the orthogonal like to the left and down states here. And moreover, if that to the upright state features with multiplicity r, then it is perpendicular to any state which features other direction at least n minus r plus 1 times. And we now can like physically formulate or interpret the Majorana states, and they are basically just the directions for which Stern-Gerlach measurement has probability 0 to find the spin to be entirely in the opposite direction. Yeah, and that's because of that picture. So you should imagine that picture, and if you point out the Stern-Gerlach apparatus in those directions, then you will get the exact direction as a pure state there as the result with probability 1. So we will have like 0 probability of getting opposite result on that sphere. Yeah, and if state is of multiplicity r, so those like r points of those n on a sphere will collect into one here, then that will mean that the probability is 0 for the m value to be anything from minus j to minus j plus r minus 1. So it will just like eliminate a lot more m values for the state to be in. Yeah, and you will see that as like disappearing m values from the bottom here, for example, like for I don't know, like a bunch of the values from the bottom on the resulting screen here. Yeah, and this representation for general n-spin states is not very familiar to most physicists. Instead, they will usually adopt the spherical harmonic approach, about which we will talk in the next subchapter. Any questions on this chapter?
Well, I had a comment about the Stern-Gerlach experiment. This was like a really foundational experiment in quantum mechanics, because it showed that angular momentum had to be quantized, right? If it were a continuously varying observable, then we would just see like a big patch across the whole screen. But instead, what we see is a bunch of like dots that are equally spaced out. And so
interesting. I did not see that in the picture.
Yeah, so see, they in part 4 they show what it would look like if it were continuously varying.
Yeah.
But in part 5, this is where it's quantized.
Yeah. So they expected to see the line, like the continuous spectrum, as on the 4 result here, but they were able to see only 5.
Right, and then for the higher spins, like what we were looking at in Penrose's book, was all of those dots are equally spaced. So that's why we get the like integer difference between the spin values.
Yeah, okay, now I see it.
Oh, play this animation on the right. That I really like these guys.
Yeah, nice animation. Okay, so let's continue.
Question here. Is this experiment the origin of the discovery of spin?
That's a really good question. They usually teach it that way in the textbooks, but I'm not sure.
Yeah, like the first time I have seen spin in the Feynman's lectures, it was Stern-Gerlach experiment.
Because I was wondering, because spin is just this physical intuition of a rotation is due to this classical imagination where it is actually just a number that somehow is influenced, a number that we measure of a quantity that is influenced by magnetic field. So that's why I wonder if this is the origin of this.
But it's connected. It's connected with the like rotations in space. So like rotation generators of the Lie algebra, they act as observables actually. So it's still connected. Nevertheless, it's quantized. It's discrete.
Well, and I think this classical picture works to an extent. Like you can make a current loop with a radius that of like the hydrogen atom, and you say the current is just one electron charge, and it goes around at whatever the ground state of the hydrogen atom is. That you say, okay, well, let's say all that energy is kinetic energy of the electron, and it's going around this current loop. Well, what you'd get is actually a magnetic dipole from the closed loop of current, and it's actually a pretty good approximation. There's a small error in it, in that they call it the anomalous magnetic moment. So the anomalous magnetic moment is just that like that contribution that is not purely classical. It turns out that it's like just a little bit larger than what you expect. But I think the reason why we use this angular momentum analogy is that it's actually a pretty close approximation if you just assume that it's a current of one electron going around at the energy of the ground state of the hydrogen atom.
Yeah, and actually at the end of this chapter 22, Penrose is actually writing a little bit about like Bohr model, for example, and how like classical intuitions were kind of tweaked to obtain the right results. And they've been using a lot of like heuristics models like that, but they had no like good theoretical underpinnings below those. And like the quantum mechanics was the first one which allowed, for example, to explain like spectral lines, like not falling of the electron on the nuclei, and etc. Like those strange, like absurd things which were not in line with the classical theory.
I will be reading, hopefully this week, those materials. Thank you.
Yeah, but it's still like only a little bit of history. So I think just by going to the Wikipedia, for example, just reading a little bit more, we can learn a lot more than from the Penrose book. So he just like scratches the surface and that's it. Okay, let me review a bit this subchapter. I just scroll down a bit, take a look, because there is pretty much material here, and I'm not sure that it's really like the first part of this subchapter is really interesting. It seems like crucial to me, but the second one is a little bit overcomplicated and doesn't seem to me like really important actually. Anyway, so Penrose told us in the previous subchapter that this Majorana picture and like decomposition for the n-spin states is not very familiar to most physicists, and they use spherical harmonics instead. And recall that in chapter 20 we talked about the classical theory of vibrations with no dissipation and small amplitudes. And these vibrations were composed of normal modes, each having its own normal frequency. And for compact objects, basically like bounded ones, we can think in the basic terms of those like that. The normal modes will constitute a discrete family. So in the case of a sphere S2, those are called spherical harmonics and can be visualized as vibrations of a soap bubble, for example. And to classify those, we need to take a look at the Laplacian operator and S2. And we have already encountered that in chapter 10, I think, where we've been talking about soap film oscillations along some like wire carcass or something. And that it is connected with Cauchy-Riemann equations actually. And probably that theorem or like problem called Platov problem. So, and it's about like optimal surfaces and it's connected with those soap bubble things. Anyway, so Laplacian is really important in the problems like that. And to compose that, we need to first obtain metric on a sphere, and in spherical coordinates it looks like that. So we have like two spherical angles here, like theta and phi. And by using that and having that like double covariant derivative here, we can obtain the overall Laplacian as this formula. Yeah, and the possible eigenvalues for that Laplacian will be minus j multiplied by j plus 1, and it starts to remind something, right? And these eigenfunctions are what is called spherical harmonics, and it is usual to demand that those are also eigenfunctions for d by d phi operator. So phi is just that spherical angle here, and in that case we will get eigenvalues which are equal Im, where m is bounded by is from minus j to j, and we will have some equation like this for describing that situation. So you probably already noticed that there is a remarkable similarity between these eigenvalues and the eigenvalues of the Casimir operator G squared and L3 operator for the m values, and in fact we can make the identification like that by using appropriate like minus I here and minus sign for the Laplacian here to get the right signs near the eigenvalues. And so like the wave function described in terms of the angles, the spherical angles, which Penrose called like angular dependence of the wave function. For the integral spin particle will be necessarily J spherical harmonic. And J spherical harmonic, it means like for that different value of J here, for different eigenvalue, you will have different eigenfunction. And in the book, he had also like some examples for the eigenfunctions, like for different J and M's there, we will get different phi capitals there. So, and they will be like some sines, cosines of theta, and some exponentials with phi used as a phase there. But anyway, you can ask, but what if the spin is not integral one? And in the half-odd case, j over 2, we will need to use spin-weighted spherical harmonics, and these will not be just the simple functions on the sphere. They will depend also on the unit spinorial tangent vector on each point of a sphere, And we can obtain that by using our Clifford bundle. We talked about in the chapter 15. And you can see that here at the end of the caption of the figure 22.17, he says that such functions are more properly on the S3, on the four-dimensional sphere, or like three-dimensional sphere in the four-dimensional space, right? Depicted, it is depicted on the left here, and it is the Clifford spin vector bundle. Probably we need to take a look at the chapter 15 here to be sure what he means by that. I haven't done that myself, so let's try and take a look further and further. Okay, so almost there. Complex. Probably it was here. So you should recall that we had a fiber bundle created of the fibers where fibers were just circles, right? And we can kind of defiber the S3 into those circles, and it will be like representation of S3 as a fiber bundle on S2, where fiber is S1. So we have a regular sphere, and at each point we have a circle, and that will give us the four-dimensional case for a sphere. Okay, and he said here that since any ordinary unit tangent vector has just two manifestations as spinorial object, we must identify two if we wish to pass from the spinorial vector to the ordinary vector here. Maybe a little bit above. So we talked here that Clifford bundle has no continuous cross sections, and to understand this, it will be helpful to look at the Clifford bundle in the another way. And in fact, it turns out that each point of our sphere S3 can be interpreted as unit length spinorial tangent vector on 2S2 at one of its points. So each point of S3 is a spinorial tangent vector to S2. Okay, and from chapter 11 we know that spinorial means that quantity change signs when completely rotated through 2p. And according to the above statement, the cross section of our bundle would represent a continuous field of such spinorial unit vectors on a sphere. Okay, and we do not have such even in case of the unit tangent vectors, so that kind of concludes that we don't have the continuous cross section. Okay, and here he says that it deserves some further discussion, that there is a good deal more to be gained from this example. Yeah, and he identifies here like the pairs of points on S3 for spinorial objects to obtain just a regular like a vector field on S2 instead of spinorial one. So spinors are kind of square roots here, you know. Then basically we have like vector and vector tangent vector to S2 will give us like two spinorial cases for it, and therefore it will give us like 2 points on S3 instead of one. Okay, so let's go back. Let's go back and let's see if we can make some connections here. So basically he just uses here the fact that the point on S3 is a tangent spinorial vector to S2, and basically that's it. And he says that a function, we will make, like, instead of just a function, we will make the function which is spin weight, has a spin weight of S, and it means that it has e to I s x or he here dependence on the angle he through which the spin vector rotates within its tangent plane to S2, and as he increases, the corresponding point on S3 will describe a Clifford circle, and probably that he will go from 0 to 720 degrees. So if you make if you will make like a 2 pi rotation, the spinor will change its sign, and in terms of Clifford bundle, that point on S3 will just make a half circle rotation here. So that's like the basic structure, and he just says that in the half odd cases we will need those more elaborate spin weighted spherical harmonics, which will depend also on those tangent vectors here on S2. And to obtain spherical harmonics from n-spin state, we will need to take like two basic one spinors, Xa and eta A here, which will represent the opposite points on S2. And they have the corresponding components as described on that figure below. And to obtain harmonics, we will need to calculate spin tensor components in this way, just like by the contraction of the indices here and substituting x's and etas at the corresponding indices, like from A to C and D to F here. And we can have different combinations of those, like take more x's or take more etas here. So the numbers of those will fix the form of the spherical harmonic here, and generally we will have that number of x's is some j plus s and etas is j minus s, where s is a spin weight for the function, probably just a number of dependencies on spinorial vectors or something. And if number of xi equals to the number of etas, we get just a regular spherical harmonic, and if not, we will have like these spin weighted spherical harmonic things. Okay, and if we use standard basis states in the place of psi here, we'll obtain multiples of standard spherical harmonics. In this case, all components will vanish except one. Okay. Yeah, and he also said that spin tensors provide n plus one dimensional SO3 representation. So the same applies for the spaces of 2n spherical harmonics here. Okay, and actually Majorana description was obtained using those spin-weighted spherical harmonics, and actually that was the fact they were originally obtained by Ettore Majorana. And those one spinors are corresponding zeros for those functions. Yeah, and he understands that this is only a brief description of the theory, but the main thing to get from that is that this new language of the spin tensors and spinors could be really useful and effective tool in research of spherical harmonics, and in many aspects of spinor formalism it is easier to be used, but it's not very familiar for the people, like in mathematics, I think, and maybe in physics also. So what in conclusion, we can say that spherical harmonics are important, and in most applications there is no particular connection to the angular momentum. So like small oscillation of a soap bubble will be an example here. Another is analysis of the microwave background over the celestial sphere coming from the depths of space, and this will have a great significance for us when we will talk about cosmology in the later chapters. And contrast between quantum mechanics and classical manifestations of spherical harmonics is striking and non-intuitive actually. In particular, a system of zero angular momentum must be spherically symmetric in quantum case, because for g equals 0, the wave function is composed from a constant spherical harmonic. But in classical physics, we know that not rotating objects could have any form, right? They shouldn't be spherical only. And in the opposite direction, we see that randomly chosen quantum mechanical system with a large angular moment, g value in that case, will have that Majorana-like peppered structure on a sphere representing its spin, which is not true obviously in the classical case, because in that case we will need to force those Majorana directions to be clustered upon only one fixed direction in space, and that's it. So we have like a really drastic difference here. And why such differences? And Penrose says that the answer is that almost all large quantum systems do not resemble the classical ones. And the famous example is the Schrodinger's cat. Why we do not see things like that at the classical level. And he says that this will be answered in chapters 29 and 30 when we'll talk more about measurements later. Yeah, and at the end, he just says that general harmonic analysis on other spaces is really important in physics, so we can take, instead of a sphere, more general spaces. But you need to remember that you should be careful while taking out some results from the compact case to the non-compact case, because in such way people often lose a lot of harmonics while transferring theories, for example, to the hyperbolic spaces. Phew. So that's it, and basically this subchapter could be subdivided in three, I think. So the first one is about these basic interconnections between J and L operators with the corresponding Laplacians and d by d phi operator. The next one is about more general case for the spin-weighted things, and the last one is about those historical nodes here. Any questions or maybe additions?
Yeah, I think the equation there with the Laplacian of phi, the eigenvalue equation that was up there, we mentioned last week the Legendre differential equation. I believe this is it.
And so we have talked about Legendre equation in terms of those like ladder operators, right?
Well, so I think it came up just as a matter of like why are J and N integers, and so the Legendre differential equation, it was around actually before quantum, I believe, but it ends up being applicable here because, yeah, could you actually pull up the Legendre differential equation? The way that we end up with integers here is that we have to do a series solution to this differential equation, and then those series diverge. Yeah, so he ends up here, finds some recurrence relation for all the coefficients in the series, and then in order to deal with these series diverging, you have to cut them off, and the cutoff points are integer values because we're still talking about like a series expansion. And so that's where they use L and N here, or in Penrose it's J and M. So yeah, I just wanted to point out that like, yeah, I think that this is actually where they end up with it. Yeah, and so this equation that's at the top of your screen right now, that is what we have in your notes.
So if you'll take a look at the Laplacian, it will have a similar form, right? Like second derivative by theta here, cosine, sine, and d theta. And here we have really similar things.
Yeah, I think this is just the case for when there's azimuthal symmetry. So like when there's no phi component.
And they just trying to kind of brute force the solution by substituting that infinite series, infinite polynomial inside.
Yeah, so you like first assume that the solution can be expanded as a power series, and then they just plug in the derivatives in this equation, and then they put like limits on what these coefficients have to be. So this last one, yeah, they end up with some series. It has to come out to be 0. So you see how we have a sub n plus 2 and a sub n in there? This makes it so that you can relate the coefficients. So if you know like the 0th coefficient, you can get the second coefficient.
So they obtained that recursive relation between a n plus 2 and a n below from that. So they just took every like constituent or child of the series here, right? And said each term must vanish, so we just get this, and therefore we should have those recursive relations.
Yep. So they end up with even and odd solutions because they're spaced by 2, right? The n plus 2 is related to the nth term. So if you know that it's going to be an even solution, then you start with like a0, and if you know it's going to be an odd solution, you start with a1. So yeah, I just wanted to point out that this is where we get the fact that they must be integers and nothing in between.
Yeah, interesting because like Penrose in his book, probably in the few next subchapters, he will talk about compactness, and that actually the crucial factor for those things like spin to be discrete was the compactness of the space they are working on. So basically, like we have a sphere for space directions, and therefore we are obtaining those discrete things or values for the spin. But if it wasn't such a nice thing like a sphere and it was some kind of hyperbolic space, we will have had like a continuum instead there. So maybe word compact should be somewhere here. No, not so easy. Yeah, so just to conclude, what we talked about today, uh, it was about the uh, like basic notion of spin here and its connection like to the angular momentum operators. The spinors arises from the like representation of the SO3 group in terms of Pauli matrices, and we could have like more dimensional representations also, and from those will arise those spin tensors of the dimension n. And we have seen in the book that we can construct something which is called like a complete commutative set of operators from Casimir operator G squared and L3. We will talk about those more in the next chapter, subchapter I mean. And we talked about the Riemannian sphere for the two-state system, and in the next subchapter we talked about how that could be used for the general n-spin state in terms of Majorana description. We also talked about polarization a bit and how the polarization form could be obtained using the Riemannian sphere and projections. We also talked about the Stern-Gerlach apparatus and that it is related to the Majorana states here. Yeah, and the connection between the spherical harmonics, these oscillations of the sphere, and our magical like spin eigenstates and eigennumbers here. Okay, yeah, and we talked at the end about the differences in quantum mechanical system. I think that's really important and pretty understandable things, right? That like it's amazing that they have so much differences in those examples, like for zero angular momentum in quantum mechanics, the spherical form, but no spherical form in classical physics for not rotating objects. And also for big values, we have that Majorana-like things where angular momentum is kind of quantized and how to say, like dispersed over different direction in the space. But in the classical case, in the limit, we should come to the one direction only. But that will not be a case for the limit of the quantum mechanical system. So it's kind of paradoxical. How could that be? Yeah, so we will learn more about that later, and we should be aware about compactness. So compactness is a really crucial thing here, and it will play its role, and we'll talk about it more later, I'm sure about that.
Sorry, yeah, the first example there, it seems to me like the spherical cow thing. That it's just an approximation, basically.
You're talking about J equals 0 here?
Yeah. The difference in the quantum and classical physics description, the non-rotating object.
It has what? Could you repeat?
Yeah. Oh, my cell phone is troubling. It sounds to me like the spherical cow description.
Yeah,
you know how we approximate. Yeah.
Yeah, so if you take J equals 0, you will obtain that this Laplacian equals to 0, right? And that phi therefore will just like describe the sphere for us, not moving. So when Laplacian is equal to 0, we just have a constant spherical theme.
But in classical mechanics, we don't have a sphere at all.
Yeah. So you just been saying that probably we have some problem with that spherical representation here, and maybe we can find some other representation or something, yeah?
Yes, exactly.
Yeah, but it works in quantum mechanics nicely. those spheres. So question
Oh,
was,
Yeah, statistically speaking, it works very well, but you know, should we be satisfied with that?
yeah, I'm sure
Statistical probability.
we will talk about those later in those chapters 29 and 30. But yeah, so a lot of things are postponed for the laters.
Okay.
So let's try and jump into the next subchapter. And in the next subchapter, we will talk about the angular momentum, but now in the relativistic and quantum terms together. So, for starters, we need to recall chapter 18, where we have had the four-vector PA and the MAB tensor. PA was representing the energy momentum things, and MAB was representing angular momentum and mass center movement. So it contained 6 independent components there. Okay, and actually that MAB tensor has the same structure in terms of symmetries as the Faraday tensor. Yeah, and also energy, I forgot the right name, like energy tensor T from general relativity. Probably it will have similar structure, but it has also diagonal terms. Okay, nevertheless, let's continue. So we have PA and MAB, and we have seen in the chapter 21 that in quantum mechanics, energy and momentum represent the generators of space-time translations. In the same way, MAB corresponds to the generators of the rotations in space-time M, and the rotations in space-time, they will mix up the space-time coordinates. So 3 of those will correspond for the usual space rotations, and the other 3 will correspond to the Lorentz boosts. So we have 3 generators for the rotations, and 3 generators which are connected with mass center movement will correspond to the Lorentzian boost generators. So they will mix up time and space, basically. And together they will give rise to the Lie algebra for the Poincare group, which is not abelian, so some of its generators do not commute. And their commutation relations will be described by the equations below, where G, I think, is just like Minkowski matrix, I think. Okay. Yeah, and we have also diagrammatic form, but we shouldn't pay attention currently to it, so it's not important, I think, because of not really popular attention or like credibility of that diagrammatic calculus, so I think we can just skip it for now. Okay, and in the previous subchapters, we've seen that for the non-relativistic angular momentum, we were able to describe basis states in terms of the eigenvalues j plus 1, and m for the observables g squared and L3 correspondingly. And that's because those two formed the complete commuting set. I will call that by abbreviation just CCS of operators for the set of generators L1, L2, and L3. So what is that? It just means that we cannot construct any other operators from the generators L1, L2, and L3 which will commute with both of those. So that's like the maximal commuting set of operators constructed from the generators. In this case, they were L1, L2, and L3. And why do we interested in those commutative operators and CCS?
Can I just make a small comment here?
Yeah.
Oh, my phone is broken. this just seems to me similar to the concept of closure in mathematics. I don't know.
Yeah, so it's like making something maximal, right? Like maximal set of commuting operators.
Well, maximum, not really. I think it's more like when you use these operators, you will always, they will be sufficient. I can't really describe it now, sorry.
Yeah, but what you meant by closure?
Basically, if I don't remember the details now, but basically if you have some operators, addition, multiplication, or so on, if you have something under closure under these operators, you will always be inside of this set while you use them. You will never go outside of it. And it seems to me, in a similar sense, these are self-confined. I don't know if this adds anything, but yeah, you seem to recognize something.
I think that's maybe that those are connected, but that's a bit other case, a bit other. So.
Well, I think they're related in that for it to be a commuting set of operators, they share the same basis, and then to be a complete commuting set means that all the operators share the same basis and span the whole Hilbert space.
And also doesn't go outside of it.
You mean that
that would mean.
Their eigenstates will form a complete basis for our Hilbert space, right?
Right.
Yeah, probably that's also true. Yeah. Not sure about this because Penrose he haven't said about this explicitly. But anyway, in the next note here,
just a thought, no need to spend much time on it.
Yeah, he said that we are interested in commutative operators and CCS because in that case we can find states which will be eigenstates for every operator in a set, in our CCS set, and the corresponding eigenvalues will allow us to label those basis states using the eigenvalues. So I think, yeah, that Joy's right here, and the eigenstates and eigenvalues here will form like a whole basis for our space. Yeah, and actually that like taking something and making it maximal in terms of some conditions, it's what is called like universal property in theory, category theory, and it's like something like making like a maximal divisor or something. So anyway,
I've never heard about this maximal thing, but can you just give a one sentence summary or something?
Yeah, you can just
possible.
I will send you a link to an article which describes this nicely in terms of mathematics, and it is called like universal object or universal construction, and usually those universal constructions will always give you some kind of maximal or minimal structure. Yeah. Depending on the category you're working on. So you can take like groups or monoids and different specifications there, or operators in this case. So I think that we can form that complete commuting set by using some kind of the universal property procedure.
Sounds interesting. I don't think I'll understand much of it, but maybe I will take a look. Thank you.
Yeah. I will send an article which explained that in terms of programming notions, and it will be more intuitive than what I have said. It's kind of hard to explain lightly. Okay, so
sure.
And in quantum mechanics we are interested therefore to get that complete commuting set of operators, and to start we usually start by finding the Casimir operators, which are scalar operators which commute with all the operators from a given system. And they're actually scalar because of the Schur lemma, and I included a bit of the book, the physics of from symmetry book here. And basically what it says here is that there are many possible representations for each group, and how do we know which one to choose to describe nature? And there is an idea that is based on the Casimir elements, and Casimir element is the Casimir operator, it's the same. So it's built from the generators of the Lie algebra of a group, and its defining feature is that it commutes with every generator of the group. And that is important also to be used in the Schur's lemma. And Schur lemma tell us that if we have an irreducible representation, so like minimalistic one, then any linear operators that commutes with all operators Rx here, so those are inside the representation, they must be scalar multiple of the identity operator. And therefore we can give the Casimir operator the corresponding constant values, and those values numbers will just number or label every representation. And as we will see, like if you read the book, these values provide us with a way of labeling representations naturally, and therefore we have the labeling for the different spins by the spin values, and spin value will fix the dimensionality of the representation, the spin tensors, etc., etc. So therefore we kind of have really powerful mechanism by describing our representations only with like one number value, and that's it. And therefore we can start to investigate the reducible representations by starting with the representation with the lowest possible scalar value for the Casimir element. Okay, so now we can ask, like, what are those Casimir operators for our new PA and MAB components? And to give the answer, we need to introduce Pauli-Lubansky spin vector, and that spin vector is actually the Hodge dual of the wedge product of M and P here, and that will define the spin around the mass center of a system. And we also know from chapter 18 that for a single particle, our M tensor equals to the wedge product of X and P. So if you put that into this as equality here with a Hodge dual, you will see that we will have like double P wedge product here. So S will be equal to 0, and the same will be in the quantum mechanical case, but it is not true for the systems which has more particles included. And moreover, for quantum mechanical systems, we spin M tensor doesn't have this simple form, and it has additional spin term. It's included in the book. It has some complicated formula in it. Yeah, and we can find that SA, our Pauli-Lubansky spin vector, our spin vector, it is always orthogonal and commutes with PA. So PA-SA equals to 0, and PU-SA here for every U, and A will be equal to 0 here, so they intercommuting the operators. Yeah, so after describing the properties of that Pauli-Lubansky spin vector S, we can find two independent Casimir operators for the Poincare group, where mu is the rest mass of a system and g squared as a familiar operator from the previous subchapters. So we will see that if we contract P, we will have C24 mu squared, and if we contract S vector, we'll have minus mu squared g squared. And to complete the set of commuting operators, we can add to the mix 3 P operators, like space momentums, P1, P2, and P3, and the component of spin vector, any one of those, say for example S3. So in total we have 6 operators, and many different other choices could be made for that complete set. And this will be important for us in later chapters, but anyway, all of those families will contain only 6 operators. The same way we have like 6 independent components for the Poincare group symmetries. Okay, and in non-relativistic case, we could obtain the similar commutative set of operators by adding energy as a Casimir element together with P1, P2, P3, G squared, J squared, and L3. So that's like for the previous theory described in previous subchapters. And it should be noted that in the relativistic case, we do not get G squared directly, but instead it is given by the formula below, using the spin vector and energy momentum vectors. And that kind of forces us to say that the rest mass doesn't equal to 0. But otherwise, if that mass equals to 0, we need to use helicity, and we need to put the physical requirement that that spin vector will be proportional to helicity and energy momentum vector. So it will be equal to SPA. And now, in that case, if rest mass equals to 0, we will have 4 independent commuting observables, which we can take to be S, P1, P2, and P3. And in fact, it turns out that by far the neatest way to handle the massless case is to appeal to twistor theory, where we will have also 4 twistor variables, Z0, Z1, Z2, and Z3, and they will nicely correspond to those observables. But that will be also later described in chapter 33. Okay, that's it. I think we can end our call for today. Any questions? Additions?
No, just thank you for today. Well, everyone.
Welcome. Then we have 2 minutes more with Alex here. Let's discuss the plans for the future, maybe. Like for the next time, what should we do?
Maybe we should bite off